Hello my dear friends. So in the previous lectures we discussed about the stress and the strain. So there are three types of stress. We studied longitudinal stress, tangential stress, which will be also known as shearing stress, and also we studied volume stress. And we studied types of strains. In the type of strains we studied longitudinal strain due to the longitudinal stress. We studied the tangential strain, or you can say we studied the shearing strain due to the shearing stress, and we also studied the volume strain due to the volume stress. What is a strain? Strain is nothing but the ratio of the change in dimension to its original dimension is only known as strain. So whenever I am applying a deforming force, a restoring force is getting generated. That means I am creating a stress on that object. As I am creating a stress, I am observing the change in the dimensions. So whenever I am comparing the change in dimension to its original dimension, that will be known as strain, as we discussed earlier. So stress and strain, you can see, both are directly proportional to each other. How I am saying stress and strain is directly proportional to each other? You can see here. It's a rubber. What I'm doing is that I'm just applying a little bit force. You can see the elongation. You can see the change in dimension. You can see the change in size. What I'm doing now is that I'm applying some more force. When I'm applying some more force, I'm seeing some more elongation. I'm seeing some more change in the dimension. Once again, I am increasing my force, and once again I am observing that there is a change in the dimension, and it is more than the before. So now the size of the rubber has been increased so much. So whenever I am increasing my deforming force, whenever I am increasing my external force, I am observing the dimension is also getting increased. The change in dimension is also getting increased. So whenever I am applying the deforming force or an external force, that means whenever I am creating the stress, as I am observing the stress, that means as I am observing the stress in the sense, the restoring force which is getting generated inside, how the restoring force will get generated inside? Whenever I will apply the deforming force. So whenever I am applying the deforming force inside the object, a restoring force will get generated, and that restoring force per unit area of cross section is only known as stress. So you can see here, as it is the F, inside restoring force is getting generated. As F is getting increasing, this restoring force inside the object in opposite direction will get increase. So whenever the restoring force is getting increasing, how the restoring force will get increased? Whenever the applied force is getting increased. So whenever I am increasing the deforming force, what I am observing is that there is a change in the dimensions. There is a change in the size of this rod, or there is a change in the size of this rubber. And as I am increasing, the change is also getting increased. So what is a change in increase is nothing but the strain. Whenever I am taking the ratio of the change in dimension to its original dimension, I am getting more strain. That means there is more change. How the more change in the dimension is coming out? Just because more restoring force is getting generated. And how this more restoring force is getting generated inside the object? Because of my deforming force which I am applying outside. That means I am creating the stress inside the object. Whenever I am creating the stress inside the object, I am observing that there is a change in dimension which is more. Right? So you can see here, this restoring force is saying that the stress is increasing. As the stress is increasing, strain too increasing. That means the change in dimension is also increasing. We can say the stress is directly proportional to strain, and this is only known as Hooke's law. What's Hooke's law? stress is directly proportional to strain. As I'm increasing the deforming force or an external force, I'm observing that my restoring force per unit area is getting increased. And one more thing, what I'm observing is that whenever I'm applying the deforming force, that I will observe the change in the dimensions. But as I'm increasing the deforming force, I'm increasing the change in the dimension is increasing simultaneously. So as I shown the example of the rubber, as I'm increasing my deforming force, you can see the change in the size is getting increased as my deforming force is getting increased, right? So that is why I said as the stress is increasing, strain is getting increased simultaneously. That is why I said stress is directly proportional to the strain. As we should have to remove this proportionality, we should have to write some proportionality constant. And here the proportionality constant is E. Stress is equal to E into strain. What is E? E is nothing but E will be known as elasticity modulus, or you can say modulus of elasticity. E is nothing but modulus of elasticity. Modulus of elasticity. So I can write this modulus of elasticity E is equal to stress upon strain. Stress upon strain. So I got the formula for the modulus of elasticity, and it is nothing but it is the ratio of the stress to its strain. Right? So E is nothing but it is the modulus of elasticity. It is a constant. It does not depend on anything. It is a property of the material. What it says? It is a property of a material. Like the refractive index. Refractive index is also a property of the material. Right? So, as whenever, if the E value is more, if the modulus of elasticity value is more, that means that object is having more elasticity. So, if E value is more, that means the object is having more elasticity. If E value is less, that means the object is having less elasticity. Right? So we can easily say by measuring the E whether the object has more elasticity or whether the object has less elasticity. Or we can compare the elasticity between the two objects that which is having more elasticity phenomena by measuring this E value. Right? If E is more, then the elasticity is more. Yeah. So how? So what is the E? That means how we can write the unit for the E? As you can know, what is the unit of the strain? Strain is nothing but change in dimension to its original dimension. You can see here. Here there will be change. Here there will be change of del x. That means what I can write in the strain? Del x. It is the change in dimension. It is a change in dimension. That means it is a change in the length here. It is the increase in the length. I can say two words for this same. See here, it is a change in the length. What I am observing now. After I am applying the deforming force, I am observing the change in the length. I am observing the change in the length. Instead of del x, I am considering it as del L. You can consider it as del x too. It's your wish. Totally, it's your wish. What I am considering it as del L. That means it is a change in the length. And I am saying the change in the length now as increase in the length. So I can call this del x as change in the length or increase in the length, both since the same. So as I can see here, it is a change in the dimension. Del L, it is a change in the length, or I can say it is the increase in the length. Upon to its original length, it is the original length. So when I am comparing the change in the length to its original length, it will be known as strain. What is the unit of the change in length? Change in length or it is length, the unit will be meter. And here too the unit will be meter. So meter cancel out. So strain is unitless quantity. Strain is unitless quantity, and it is also a dimensionless quantity. As it is unitless, that means it is dimensionless quantity. Right? You can see here strain is equal to del L upon L. So both there. That means L, it is also meter, it is also meter. So it is a unitless quantity. You can see here the strain. You can see the stress. What is the stress formula? Restoring force per unit area. Restoring force per unit area. What is the formula for the restoring force? What is the unit for the restoring force? Newton. And area? Meter square. So Newton per meter square is the unit of the stress. So what is the formula for the modulus of elasticity? Is equal to stress upon strain. Strain has no units. Then the whatever the unit which is present in the stress, the same unit will be applicable for the modulus of elasticity. That means modulus of the elasticity is equal to Newton per meter square is the unit of elasticity. Unit of E is equal to Newton per meter square. Right? It is about elasticity. So as we studied 3 types of stress, what is those 3 types of stress? Why we studied 3 types of stress? Because whenever we are applying the deforming force, we are trying to change the size or the shape of the object. It is what our intention is. As I am applying the deforming force, my intention is to change the size or the shape. See here, you can see this spring. You can see this spring. Yeah, what I am doing now is that I am just applying a deforming force. I am just applying the deforming force. You can see the change in the length. You can see the change in the length. But if I am applying the deforming force more than a certain limit, you can see it is getting permanently deformed. It is not coming back to its original position. You can see here, it got permanently deformed. So what I am saying is that up to a certain limit only, the body will come back to its original position even though we are applying the deforming force. If the deforming force is more than the limit, more than the elastic limit, because every elastic object will have certain limit. After that limit, it will get permanently deformed. You can see this example of the spring which I shown now. Whenever I am applying some certain limit of elastic force, whenever I am applying some amount of deforming force, you can see the spring is coming back to its original position. But once I am crossing the limit of the elasticity, I am observing that it is getting permanently deformed. Now the spring is permanently deformed. So from this I can say, up to the certain elastic limit, how much ever the stress I am creating, that much amount of stress I will get. That much amount of strain I will get. Right? How much amount of stress I am creating, how the stress I am creating. Whenever I am applying the deforming force, the stress is getting generated inside. How the stress is getting generated inside? Proportional to this deforming force, exactly opposite to that, a restoring force is going to get generated inside the body. As the force is getting increased, the restoring force inside the object will get increased. That means the stress will get increased. As the stress is getting increased, right? So that means the restoring force per unit area is getting increased. As I am increasing the deforming force, I am observing one more thing. The change in the length is getting increased, as is shown in the example of the rubber. What I am observing in the second thing is that whenever I am applying the deforming force, change in the length is getting increased, right? And it is coming back to its original position too once after the deforming force is removed. But up to a certain limit, only it will be applicable. After a certain limit, what will happen is that how much ever you are going to apply the deforming force, how much ever you are going to increase the deforming force, as once the molecule or once the object is permanently transformed or permanently deformed, then you cannot see more strain, you cannot see more change in the dimension. So the stress is directly proportional to strain only up to the elastic limit. Within the elastic limit, the stress is going to be directly proportional to strain. We will study this once again in a stress-strain curve. In that stress-strain curve, we will come to know up to the within elastic limit, the stress is directly proportional to strain. So you can see here, it is looking like y is equal to mx. You can see here, stress is equal to E into strain, y is equal to mx. If someone is asking you what is the slope of the given graph, by giving the stress and strain graph, everybody knows it is straight line from the origin. It is a straight line from the origin. Y is equal to mx means it is a straight line from the origin. Otherwise, I will draw here. See here, it's the stress, it's the strain. What I am doing is that, see here, as the stress is getting increased, I am observing the change in dimensions is also getting increased. As the stress is getting increased, I am observing the change in dimension is also getting increased. So that means whenever the stress is getting increased, strain is getting increased, that means stress is directly proportional to the strain. That is what I wrote here. And stress is equal to E into strain. If I am asking, say me, what is the slope of the straight line? What will say? M is equal to E. It is nothing but stress upon strain. You can find out the slope of this graph. Right? So in this method, maybe a question can be asked. Right? Yeah. So if someone is asking by giving you the graph of the stress and the strain, which is a straight line, and saying you to find out the slope, then what is the slope of the straight line? It is nothing but stress upon strain. And it is nothing but, stress upon strain is nothing but, it is the modulus of elasticity. As we studied 3 types of stress, as we studied 3 types of strain, like the same now we are going to study about 3 types of elasticity. What? Now we are going to study about 3 types of elasticity. Yeah. Types of elasticity. First one. So, what is the formula of the elasticity? Elasticity is nothing but it is the ratio of the stress to its strain. So, as it is stress to its strain, I have studied longitudinal stress and longitudinal strain too. So, whenever a longitudinal stress is getting created, we can observe the longitudinal strain. We can observe the longitudinal strain. We can observe the longitudinal strain. So here the modulus of elasticity will be known as Young's modulus. In a longitudinal stress and the longitudinal strain, whatever the modulus of elasticity present for the material, whatever the modulus of elasticity is given for the material, that modulus of elasticity will be known as Young's modulus of elasticity. And it will be represented as Y. So it is represented as Y. So what is Young's modulus of elasticity? It is for the if there is a change in its length, if my force is acting along its length, if I am observing the change along its length, if I am observing my restoring force is acting along its length, then at that time I will use this Young's modulus of elasticity. So Young's modulus of elasticity is nothing but longitudinal stress upon longitudinal strain. And its representation is Y. We studied shearing stress and shearing strain too, in which we observed the relative displacement whenever I am applying the deforming force parallel to the area of the cross section. Parallel to the area of the cross section, we can solve some more here. What is the longitudinal stress? It is nothing but the restoring force upon area. As you know, the restoring force will act here perpendicular to the area of cross section or normal to the area of cross section. If you don't know, please, that means if you don't know, you can see the lecture number video 2. From that you can understand how I am saying this restoring force is perpendicular to the area of the cross section or normal to the area of cross section. So you can visit the lecture number 3. You can come to know what is the reason here and how I said that this restoring force is perpendicular to this area of cross section. And what is longitudinal strain? Longitudinal strain is nothing but you can see here. What will happen? There will be a change. There will be a change. And there will be a change you can observe. So you can observe there is a change whenever I am applying the deforming force from both the ends. So you can observe the change in the length. As you are observing the change in the length, so whenever I am taking the ratio of the change in the dimensions to its original dimension will be known as strain. Here what is the strain? Delta L upon L. As there is a change in the length, as there is an increase in the length. So delta L upon L is the strain. I am writing here the strain delta L upon L. So it will come in the denominator. So it will go to numerator. So FL by A into del L is the Young's modulus of elasticity formula. So Young's modulus of elasticity is equal to FL by A into del L. What is this A? Area of cross section. Del is the change in the length, or you can say increase in the length whenever I am applying the deforming force. You can see here it is the L, it is the original length. FR is nothing but the restoring force. Our second example is that our second type of elasticity is known as shear modulus of elasticity. Shear modulus of elasticity, and it has one more name, rigidity modulus of elasticity. Rigidity modulus of elasticity. Rigidity modulus of elasticity. Here, as you can observe the shearing stress and the shearing strain. So shearing stress upon shearing strain is only known as shear modulus of elasticity. So it will be represented as G. So G is equal to shearing stress upon shearing strain. So shearing stress upon shearing strain is nothing but rigidity modulus of elasticity, or you can say shearing modulus of elasticity. And what is shearing stress? Shearing stress is nothing but restoring force upon area. See, stress has only one definition. How much amount of internal force is getting generated whenever I am applying the deforming force per unit area of cross section. Per unit area of cross section is only known as stress. Once again, whenever I am applying the deforming force, how much amount of internal force is getting generated inside the area of cross section? Inside the area of cross section is only known as stress. So whatever may be the object is, whenever I am applying the deforming force, a restoring force is going to generate, and that restoring force per unit area of the cross section is only known as stress. So stress is going to be the same, but the strain will vary, because whenever I am changing the size, it will along its length, that means it will come under the length. Whenever I am changing the shape, you can observe the theta. Whenever I am changing the volume, you can see the change in the volume, right? So strain will vary, strain formula will vary, right? But strain have one concept, that means strain has one constant definition. Whenever we are taking the ratio of the change in dimensions to its original dimensions, dimension is in the dimension, everything will come, whether it will be size or shape or it may be anything, right? So if I am observing the change in dimension, so I should have to consider the original dimension. Whenever I am taking the ratio of the change in dimensions to its original dimension, I will get the strain, right? Okay, so you can see here shearing stress, a restoring force upon area. And what is the shearing strain? Shearing strain is nothing but we done in the previous class, delta x upon L. Delta x is the relative displacement, L is the length. You can see here what I done is that here is the cylinder, here is the cylinder which is tightly fixed. What I am applying is that I am applying the deforming force. I am applying the deforming force parallel to the area of cross section. I am applying the deforming force parallel to the area of cross section. So whenever I am applying the deforming force parallel to the area of cross section, the position of the cylinder has now been changed, and it is making an angle theta with the initial position. And it is making an angle theta with the initial position. It is the length L, it is also the length L, and it is the relative displacement. What I am observing is that means it is a change in the position. So it is a change in the position is something called del x upon L. You can see here, and it is del x upon L is nothing but theta. So tan theta is equal to opposite by adjacent del x upon L. So whenever I am taking the tan theta, if the tan theta or sin theta, if it is less than 10 degree, then what I will consider is that theta, tan theta will be equivalent to theta. Whenever the theta is very less, whenever the theta is very less, I will consider the tan theta as theta. I will consider the sin theta as theta. So if the theta is very less, then the tan theta will be equivalent to theta, and the sin theta will be equivalent to theta, and I done the same here. Tan theta is equivalent to theta. As the tan theta is equivalent to theta, that means del x upon L is equivalent to theta. That means del x upon L is equal to tan theta. As tan theta is equivalent to theta, whenever the theta is very small, so del x upon L will be, we can write it as theta. Del x upon L, we can write it as theta. So instead of writing the del x upon L, I can write it as Fr by A. That means restoring force upon unit area of cross section into theta, and it will be known as shearing stress, or you can say rigidity modulus of elasticity.